I've written out the Schrödinger equation, the radial part, in the case of a central potential here. So this is just a repeat, and I've labelled it star circle. Okay. Now, so now we're trying to find what this big R term is, just sort of following on from the previous session. So let's assume R takes the following form. Now we got this as from the previous session. So that's in the limit. So let's assume this R will take this form with another factor. So it's an assumption. It's a hypothesis. And as usual, you justify it by its consequences. You know, does it work? Does it make predictions? You know, if this R is of this form, that will have certain consequences, and ultimately, do the consequences match the experimental data? It's a theoretical, observational science, right? It's quite amazing what theoretical physics can do, what it can predict, right? Okay, so assume R does take this form, plug this value into here, apply all these operators, you know, differentiate all this stuff, you know, according to this left-hand side, and I've asked you to do this as homework, and derive the following formula. Okay. So from this, assuming this, get this, right? And I've labelled this formula here just plus circle. Right? Now, in future texts, when there are more equations and more equation numbers, instead of using this kind of thing, I've said this earlier, I think I'll just use equation numbers. I'll use actual integers, and decimal points, and like 3.52, the 52nd equation of chapter 3, that kind of thing. Expect that, you know, in future courses. Right. Okay, so you know, as usual, wave mechanics boils down to solving differential equations, and here we are again in a same situation. So how to solve this? Because, you know, it's quite complicated. Now, f is obviously a function of rho, and you've got rho's underneath. You know, it's complex. So how do you start? Well, we've done this kind of thing before. Let's assume that f here, which is a function of rho, can be written as a weighted sum of powers of rho. So of this form. Okay. So a weighted, you know, you've got these coefficients of powers. So these i's here are just integers, right? So powers of rho weighted by, you know, some coefficient, and then the whole thing, you know, all these weighted powers of rho are summed. Okay. And let's assume that the highest power here, it won't go on to infinity, but let's assume you know, there's a greatest power here. Let's call it k. Right? Let's also assume that this coefficient here for the highest power is 1, right? Just for convenience. Okay? Alright, so we have this equation that I called plus circle. We're assuming again f can be written as a weighted sum of powers of rho, right? Integer powers. Right? So take that expression, plug it into here. To plug just means to substitute or just put. You know? So put this here. Okay. And well, you'll differentiate it twice with respect to rho, you differentiate it once, you'll be dividing it by rho and rho squared, etc. So now the coefficient, now what work all this out, and then have a look at what you get, and have a look at the highest power of what's left over. You plug this F, you plug this into here, calculate it through, but you only need to bother, have a look at the highest power of rho that in what's left, in the result of this equation. And the highest power, now if K is the highest power in F, what's the highest power of rho in this? We'll see, it'll be, can you see that it'll be rho to power K minus 1? So you've got an F here, so it'll have rho to K, but divide by rho, so you'll get rho to power K minus 1 from here. And is that it? Is there any more? And you'll get another one from here, right? So if you differentiate this, you'll get a K. If you're differentiating this, you get this the highest power, remember? So you've got a K here. So differentiate, you get a K, coming out the front to rho to the K minus 1, and you got a minus 1 here. So you'll get a minus K that comes from here. Minus K, and you'll get a lambda minus 1 from here, from this term, because this F will have a maximum power of rho to K divided by rho, so that'll be a power rho to K minus 1. Right? So you've got two terms. You've got a minus K from here, that's this, and you'll get a lambda minus 1 from here. These. Okay? So add those two. So that will give you your coefficient for lambda to power K minus 1. Now all these coefficients, it's an equation, right? This is all equal to 0. Now rho can vary. So the only way you get all this left-hand side equaling 0 is if all the coefficients of these, the various powers of rho from here, all those coefficients disappear. They all become 0, right? Well, what's the coefficient of a K minus 1? Well, we just did it. So it's minus K plus lambda minus 1. So that has to be 0. And that puts constraints on what lambda is. That means lambda is K plus 1. Okay? Because that's 0. So lambda is K plus 1. Now what's K? K is an integer, right? Now what's lambda? We have to go back a session or so. Lambda, I think, was defined, let me check the textbook, I think it was defined as the square root of the energy plus other factors. Let me just check. So lambda was lambda. It's complicated. There's a whole bunch of constants, and in the denominator is alpha. Now alpha in turn is defined, or alpha squared in fact, is defined as constants times the energy. Right? So if you've got a formula for lambda, and we have now, lambda is K plus 1, K is an integer, so we've got restrictions on what lambda can be, and that will in turn, with two steps removed, will put restrictions on what the energy can be. So we have found, indirectly, but we've found values for the allowed energies, the quantized energies. Quantized because lambda is going to be an integer. It can't be a real, well, can't be it's an integer, right? Lambda has to be an integer. Okay? So that will give you, now notice this lambda here, this lambda here is independent of L. There's no mention of L in this value of lambda. So the eigenenergies, the eigenvalues for the energy, this is what it works out to be. Pretty much the same as in chapter 4. So you have these the eigenvalues for the energy for all values of L, because this lambda here is independent of L. And remember what L was? It's the the allowed angular momentum, right? And this energy, the eigenvalues, are independent of L. So now, since you can have lots of different values of L, right, they're integer values, and so you have a degeneracy here, because all these states with different values of L, they all have the same energy. So the eigenfunctions of the energy, they will be degenerate, right? So you can have different eigenfunctions corresponding to different angular momenta, but the eigenvalues, the energy, independent of L. So you'll get degeneracy. You'll have eigenfunctions, different eigenfunctions corresponding to different angular momenta, but having the same energy eigenvalue. So hence degeneracy, definition of degeneracy. Remember, we've said this several times, but reinforcement's good. What is degeneracy? Degeneracy in general is when you have different eigenfunctions for the same eigenvalue in an eigenequation. Okay? Different eigenfunctions for the same eigenvalue. In this case, the eigenvalue, the energy eigenvalue, is this, and you can have different eigenfunctions with corresponding to different values of L. But those different eigenfunctions with different values of L all have the same eigenvalue for the energy, right? So in that sense, they're degenerate as far as the energy is concerned. Okay. Now this, what I've just said, it's sort of an accident that the L does not appear in the lambdas. It doesn't appear in the energy.